Hi students, welcome back to your physics class. So in our previous sessions, we discussed regarding conservation of linear momentum in case of variable mass, that is in rocket, as well as we have discussed regarding the concept of torque and as well as what is angular momentum. So in this session, so we will obtain a small relations between angular momentum and torque, and as well as we'll discuss about the law of conservation of angular momentum with an example. Okay, so already I have told in a previous class what is the linear momentum as well as angular momentum, and another term is torque. So what do you mean by your angular momentum? The momentum, linear momentum of a particle about a what? A fixed point is nothing but what? Angular momentum. Or you can say what? The angular momentum of a particle is the moment of linear momentum about a fixed point is called as the angular momentum of that. Okay, that is designated by a symbol of already what is some books in they are mentioned by C alpha E. It is what J R what again it is the angular momentum of a particle about a fixed point is nothing but what the moment of your linear momentum equal one. The moment of linear momentum about a fixed point is nothing but what angular momentum of that point. Okay, so that is specified by symbol LRJ, that is equals to R into what is T. The next I have defined your what torque tau, that is designated by a symbol of what is tau. So it is the what time rate of change of angular momentum of a particle about what a fixed point is known as and what torque. What is that's we're getting an expression. So is equal to it is d of j divided by this what T. So there j is what the angular momentum that already you know it's that's why it is defined as the time rate of change of angular momentum of a particle about what a fixed point. It is nothing but what. So now let us how to obtain what relation is existing in between your what angular momentum and what is your another term is what torque. So for that I consider what particle of mass m rotating with a velocity v about a what fixed point. Let r be the position vector of the particle, then the angular momentum of the particle is given by that we know j is equal to what r into t, where that's t equals to what t is linear momentum, t is equals to what m into p is there. So here I have written j is equals to what r into p. So when you differentiate this one with respect to t, by getting what dj by dt is equals to d by dt is equals to what r into p. So now by using your u into v method, it becomes what dr by dt into p plus of r into dt by dt. But dr by dt is nothing but our what velocity, the change in displacement with respect to time is called as velocity. So r into what m into v plus of this is what r into dt by dt. Where according to the vector notation formula, so v cross v is equal to 0, that's why I'm writing what r into dt by dt. So that dt by dt is nothing but the rate of change of the what momentum, nothing but in a force. That's why the tau is equal to what r into v of x. But dj divided by dt nothing but in tau. This is a small relations is existing in between what the torque and what the angular momentum. Tau is equal to dj divided by dt. Okay, so this is about the relations between angular momentum and the torque. Now let us discuss another important concept in your conservation law is law of conservation of what? Angular momentum. So in our previous sessions, in the beginning of the chapters, I have stated your what is the statement of your law of conservation of linear momentum. So that states that what? In the absence of any external force, the total linear momentum of the system remains what it is constant. Remains is what? Conserves. That the total linear momentum system is what? Conserves. This is a statement of your law of conservation of linear momentum. So there, how that linear momentum gets conserved. So there you are getting an equations. F is equals to dp by dt. If f is equals to 0, then you are getting what? Dp by dt is equals to 0. This dp by dt is equal to 0 when your what? The p becomes what? Constant. When the p becomes constant, that during that time only you are getting what? dp by dt is equals to 0. In the same way, so here also the torque tau is equals to what? dj by dt. Okay, tau is your what? External torque. So there, in case of linear momentum, instead of tau, you are having about f is equals to what? dt by dt. But here is tau equals to dz divided by dt. So that's why if tau equals to 0, that's in the absence of any, if there is no external torque acting on the what system, then you are having what? The tau equals to 0, then you are having what? dz divided by dt is equals to 0. This dj by dt to 0 only when the j is what? A constant. The angular momentum of the particle is what is constant about a of its. So by seeing this one, you can state the law of conservation of the what? Angular momentum. In the what is in the absence of any external torque acting on the system of particles, system of the what? Particles, the total angular momentum of the system remains constant and what? Conserves. Okay. So that is a statement of your law of conservation of angular momentum. Or what it is? In the absence of any external particle acting on a system of particles, the angular momentum, the angular momentum of that particle is what is conserved, or is it body or a system of particle is what conserves. But in linear momentum, in the absence of what external force acting on a system, the total linear momentum of system remains what is constant. Here, in the absence of external torque acting on the particle, it is what the total angular momentum of the system remains constant. Okay, I will conserve. There is a statement of the what law of conservation of angular momentum. So let us see here where you are observing the angular momentum gets conserved. That is in the motions of planet in its orbit, there the angular momentum of all the planet gets what conserved, or as well as remains constant. Suppose one simple example that we take it is a person or a man uh, holding, or we can possibly take the person or the man standing on the rotating table with dumbbells in his hand. So he's having what? Dumbbells in his hand, stretched with his hand stretched on a rotating table. After some time, a certain period of time, that person is stuck in a slow rotatory motion, and after that, if he drops his hands, suppose if he drops his hands, then what happens there? The rotation increases rapidly. Why that rotation gets increases? That is because of the what? Uh, total mass of the system remains constant, but when he drops his hand, what happens? The distance of the dumbbells from the axis of rotation gets reduced with your what R gets reduced. That means you are having moment of inertia. I equals ma square, but when he drops his hand, the value of your R gets decreases. Okay. Correspondingly, the moment of inertia of the system gets what it decreases. Okay. It depends upon the what distribution of the mass about the what axis of rotations. According to the law of conservation of angular momentum, I omega remains constant. How? But here I gets decreases. Why? How that I gets decreases due to the decreasing distance of the your what dumbbell. Distance of the dumbbell from the axis of rotation gets decreased. The R gets what reduced. R gets reduced. So that I is what decreases. But how that J is equals to I into omega. But when I decreases, automatically the value of your omega is what? So how much of your I is decreases the same amount of what omega is. So that the J equals to I into omega. The I into omega remains constant. Okay. That is the law of conservation of what angular momentum. Okay. Next, another one more important example for your law of conservation of angular momentum is the motions of the Earth under and what motions of the your what Earth around the Sun is under gravitational force. Gravitational, it is what force, which is a central force. But whatever that your gravitational force is there, that is your what central force. The angular momentum of the Earth moving around the Sun or around the Sun is conserved. Whatever the angular momentum of the Earth is there, it is what conserved while moving around the Sun. Okay, how it is conserved, even though that velocity and the angular velocity of the what Earth goes on changes at particular point. So here, when the Earth is at the what perihelion at that stage, it means that the Earth is closest to the Sun. During that time, the angular velocity of the what increases. When that your Earth is aphelion, that is far away from the Sun, in such case, the angular velocity is what minimum. But the total angular momentum of that Earth is what comes out while moving around the what Sun. Okay, so this is these are the examples of the what law of conservation of angular momentum. Okay, so in this class, what I have discussed is I have discussed what the relation is existing in between your angular momentum and torque. And next, I have stated your law of conservation of angular momentum, and I have proved that how that the total angular momentum of the system remains constant in the absence of what a total external torque. And I have given some examples regarding where that the angular momentum remains constant. Okay, thank you.